Okay, now we're into our next segment in general ecology. And for this segment, we're going to get a little bit into the nitty-gritty of data analysis. Last segment, we were looking at experimental design with some data that were coming out of my master's. I'll probably come back to that project during the course of this semester periodically. But this one is going to be a little bit more quantitative, just the nuts and bolts of statistics, really. But not just statistics. There are other things you do with your data beyond stats. And I want to kind of give you some theoretical underpinnings so that you can use these techniques for this class. Hopefully some of you have had stats already. Those who haven't, you're not at a disadvantage. You may have a little extra work to do, but you don't need to learn the stats per se for my class, okay? You do need to learn how to use it, at least in your lab manual, your lab write-ups, sorry. But understanding why the result that you get tells you what you think it's telling you. In other words, the real nitty-gritty theory behind that statistic is not my goal. My goal is for you to see that type of analysis in, say, a paper you're reading, and be able to say, oh, yeah, okay, I believe them. They've told me that there's a difference between, remember these two shrubs, Arctostaphylos and Adenostoma, for Douglas fir survival. And I see the stats that they did, and I think it's legit, right? Better if you really understand the stats, but you'll get that as you move ahead in your career. So today is about data analyses. And yeah, there is a condition in biology called math phobia. I probably shouldn't say that because some of you are probably going, yep, that's me. And you turn off. Don't turn off, okay? Work with me on this one, and it'll only help you. There's an abacus there and a guy whose head is bursting, whether it's because he doesn't understand how to use an abacus or because he's getting incredible numbers that he's just doesn't know what to do with them. You've all been here, right? So here's a set of data for a species of iris. I didn't pull all the data out. I just have iris setosa information, petal width, petal length. And there were 3 other species in this data set, but I just have a little bit. Can you imagine typing in all those numbers to find out what the average sepal length is over here? I've got a new laser pointer here. From 5.1 all the way down, you got to type those in, and if there's a series of 4.9s, you better get them all. It's not a pleasant experience. If you're doing it on your calculator, guaranteed you'll make mistakes if you've got lots of data to enter. So the trick is, this is where I want to emphasize it, learning how to use Excel, and I'll have a presentation on that later. Learning how to use Excel is huge because you can avoid those data entry mistakes, okay? But let's say we want to calculate the mean length of the sepals or the petals of our different species of iris, okay? And we'll come back to this data set, but this is sort of the crux of what today's presentation is about. These are, at this point, these are called descriptive statistics. You're using the data analyses to describe what these data are about. You can't look at that big table and get a sense of what the average sepal length is. I mean, you can. Maybe it's 5. So if we go back, yeah, maybe it's 5, maybe it's 4.8. Don't really know until you plug all those numbers in and calculate the average, okay? And that average is a measure of what I call the central tendency of the data. A single number tells you what the central tendency, what the typical number might look like. If you were to get a whole group of data, you'd have a good understanding of how of where the central tendency is. I don't have a better word for it right now. But there are 3 different variations. The mean, you know, that's the average. The mode is the number that occurs most frequently. So in that sepal experiment or data set, it might be 4.9 occurs 10 times and no other number occurs that many times. That tells you that 4.9 seems to be a pretty important number and gives you an indication of the central tendency. The median gives you the middle, right? The median strip in a freeway or throughway, depending on where you come from, is the middle strip between the two lane, traffic going one way, traffic going the other way. That median is the middle. And the median in the data set is the medium number. So you could take the high and the low and you get that average, that median in the middle. All of those should be roughly the same number if the data are normally distributed like a bell-shaped curve. Okay, and I'll show you an example of this in a minute. The other descriptive statistic that is very important is the spread. So you might have a bell-shaped curve. If we could go back, I'm sorry. If you had a bell-shaped curve that looks like this, extremely steep and then goes out like that, then you don't have much of a spread, right? They're all right around the median, the mode, the mean. I almost said average. But if maybe the spread looks like this, that's a very different set of data, okay? Real steep, real spread in the bell-shaped curve. So that's where we get an idea of the spread, and we have measures, the range, the two endpoints, the variance, and we usually use standard deviation, standard error of the mean, standard deviation of the data, standard error of the mean. And that's basically looking at how different the data points are from whatever measure you're using, let's say the mean. So each data point has to be a little bit off the mean. Some might be right on the mean, and then there's no spread on those data. But overall, you get that impression of how spread your data are. And that's very informative. And you could use it for additional statistics down the road that are not descriptive, but more comparative between two data sets. So, okay. Central tendency and spread. I could see a future question on some kind of exam. Give me 3 examples of a central tendency or the spread, right? You should know those terms. What's the range? What's the variance? What's the deviation or error of the mean? Okay, so here's the mean. This is how you calculate it. And you could do it in Excel or you could do it by hand. But again, getting the mean by hand could be a monster if the data set is big. So to calculate it, you all know this, the average, it's the sum. This is a Greek letter for S, sigma, of all the data points, I, divided by the total number of data points, and that's your average, you know that, right? The mode is the most frequent value, and the median is the middle value. I've already given you that information. Okay, and here you get an understanding that when the data are not normally distributed, they're skewed, then the mode, the median, and the mean give you different numbers. And that spells trouble. I mean, there's things to do with that. That's okay, and the data are what they are. But a normally distributed data set you could use any of those numbers. And then if it's skewed, then which of those central tendency numbers you would use depends on what you're trying to discuss, okay? If you're discussing the typical salary or income, annual income of an American, then you probably don't want to use the mean. Yeah, so you have some people that are way out on the ends. And so the mean doesn't give you information and if you look when they just report typical income, annual income of US citizens, it's usually the median that they report because that's a better reflection in a skewed data set of what the sort of average, well, I didn't want to use that word, the central tendency is, okay? There's a lot of people that don't have very big salaries. There's a few people that have huge salaries, right? Okay, let's move on before we have to dwell on that much further. So now we want to know about the spread, and as I said, these are ways of looking at the any one data point, how far away is it from that central tendency that you've come up with, let's say the mean. You could do the range, the highest and the lowest. You could do the standard deviation. This one's a little more complicated. S equals, the standard deviation equals the sum of all the data points minus the mean. So there's that separation. How far away is the data point from the mean? And then you take all of those and square them. And then you take the sum of that number, divide it by your number of samples in the study, n, minus 1. And I'm not going to get into why that minus 1 crops up. And then you take the standard, square root. That gives you s, the standard deviation. The variance, just square that s. And then the standard error of the mean, which is how most people report their spread, or many people do, is just s, that is the standard deviation, divided by the number of samples, the square root of the number of samples. And that gives you sort of the understanding of how close is your calculated mean to what you would get if you went out and did it again. Are you going to get a mean that's pretty close to that? Then your standard error should be pretty tight. Are you going to go out and take it again and get something way off scale on that figure? Then it means that your variance is really high and you don't have a very good understanding of that mean actually because there's too much spread in your data. So, okay. Here's a couple of examples. This is a data set that looked at the price of vehicles when you leave the lot. So brand new is in blue for a compact car, might be around $5,000. I bet this is an old data set. As soon as you drive off the lot, you can't sell that for much more than $2,500. All right. If it's a large car, obviously it's going to be worth more. And there's a bigger drop in value when you drive off the lot. So I know compact cars are really cost efficient. And then there's median cars that are somewhere in between, medium cars. So this shows you the averages of each of those groups. But you look at those and you say, well, is it statistically significant, the price difference between in a compact car between brand new and right off the lot? The error bars seem to overlap. So here I'm trying to express to you that actually the visual impression here is only comparing each individual bar and its spread, each individual average and its spread to the other one in that category. Okay, you can also do stats where you compare across all of them, but we're just doing these pairs. And visually it looks like there's an overlap of those means, those averages. But that's just a visual impression. You're actually not comparing the data in what I like to say is comparing the data within a single equation that allows you to say, is brand new really different from, is it a different population of numbers from right off the lot? And we'll come back to that in a minute. That's an important statistical tool that we will use in this lab. Okay. So my point here, looks can be deceiving. These don't look significantly different. These do. We'll look at that in more detail in a bit. So let's do that. Let's explore this a bit more. But I have some other ways of also some other things I want to get across during this little segment. So here, every single study starts with an observation, right? And here's my observation. And at this point, sometimes people start to wiggle in their seats a little bit. But I've been teaching this course enough, and I did make this slide this my first year. Grades in this class will vary from F to A. It's a big enough sample size I can be confident every year that happens. The causes for the different grades is another story, but definitely that's the spread of the data from F to A in EFB 320. So here are some hypotheses that might are ways of, here are some ideas that show you what hypotheses are. The first, you can have a predictive hypothesis. I'll come back to this in a minute, but the predictive hypothesis here, you can think of why, or what I would come up with. I wouldn't be so naive to say is that you have to hear all my lectures to get an A, But I might suggest that reading the textbook helps. Coming to the lectures helps. Getting on the web helps. These are predictions. If you do these things, the predictive hypothesis is you move towards the A and away from the F. Coming to class normally helps. Taking the exams definitely helps, as opposed to missing them for some reason. So examples of hypotheses. I showed you the predictive hypothesis for the grades in the class. Here, I'm predicting COVID-19 will spike again in the fall. It's an educated guess. And I pay attention to people like Fauci, Dr. Fauci, who is a scientist and has some pretty good, cogent arguments as to why this will behave like the 1919 coronavirus or flu virus. The null hypothesis would be there will be no difference between the numbers of infections this summer, where there would be fewer, and in the fall, except as one might predict by chance alone or by sampling error, right? So there's going to be this increase is the prediction. That means what we're saying is that there's going to be a difference in the population of infected people in the summer, now, where the infections are going down, and then in the fall. One could also do the two falls. There will be no difference in the spread of the virus this past spring, and in the fall. And the argument is, no, it's going to spike again. And so in that case, there will be no difference for the spring. And you have to accept the null hypothesis because they're both high. Infection is high again. It means a lot for how we deliver our lectures and such. Okay, there's always going to be some difference. So on this slide, you can see that it says except what happens by chance or sampling error, just who you pick. Like if you only go to rest homes, you're liable to get a lot more infections than if you only go to soccer games of the youth to do your sampling. That's going to be two different populations. So that's a sampling error, right? Not by chance. Bias. Okay. Hypothesis, one way to look at it is it's an explanation made on the basis of a limited amount of evidence as a starting point for further investigation. Go back to Karl Popper. We say, we think this is going on. We're going to do some experimentation and statistical testing to see if our explanation is sound. And that's what Popper gave us. You can't just make that explanation and call it good. Okay, so here's one of my predictions. Students that are engaged in class earn a better grade than those that are not. Not entirely. There's going to be outliers that don't need to do any of this. They already know it somehow. I kind of doubt it, but there could be, right? And so even they, though, could probably get a better grade if they are more engaged, even to the extent of learning what my biases are and what I'm liable to emphasize on a test, for instance, okay? Okay, and the null hypothesis always tests a statistical difference between groups, as I said. The difference between samples from group A and group B will be no greater than chance alone. And in other words, the samples came from one population, no difference between the two groups, or two populations. You've actually got two different populations. And I guess the example I just used is COVID infections in a nursing home, COVID infections in a soccer league, right? Local soccer league for your kids. Sorry, my kids, your siblings. Okay, and here's the null hypothesis for our grade example. The difference in the final grade of those that were engaged would be no different than that expected by chance alone. And what do I mean by engaged? That's actually a horribly written hypothesis because that word engaged is pretty flexible. But one might explain in their paper that what they're referring to is people that come to lecture, for the lecture as opposed to doing emails, scan text before the lecture and read it, even better, after the lecture. Oh, that's what he was talking about. Well, now it makes sense. Apply the ideas outside of class. That's when you start to synthesize and really get to internalize the concepts, and they become your own. That's wonderful. And then obviously study for exams. Everybody does that, but it doesn't all, to some degree, not the night before. Study a little bit earlier, maybe. Okay. So how do you test the null hypothesis? Note, sorry to flip back and forth to this one. We're testing between two groups, two populations. So, sorry, if we look here, we've got two different groups, or two, what we call in the number crunching world, two populations of data. Or are they a single population? If it's a single population, you'll accept the null, there is no difference. If it's two populations, you'll see dramatic differences in the mean, and the spread of the data will support that they are two different things. And you've been able to dig in and reveal that in this example of a statistical analysis. We will use in the class, the best one I think is called the student's t-test. It's what's known as a parametric test. It uses parameters, and the two parameters are the mean, usually, but you could use the median if there's reason, and the standard deviation, sorry, 3 parameters, and the number of samples, okay, of both, of all your data, of both your groups that you've sampled from. It's called parametric because those are all parameters. You can't always do that for a variety of reasons, so sometimes it's better to go to non-parametric tests. That means in the chi-square test, for instance, which you will use in this class again, you might use frequency data instead of the mean. But we'll show you where to use those and when to use those and how to interpret them when it's time. So let's go back to this example. If we were to do a t-test, now I'm making this up big time, all right? So just allow that. But we're wanting to know within each of these groups, are the two sample sets of the compact data statistically significant or not in a t-test? Are these two different? And then are these two different? We're treating them as 3 different tests. So that would be how you would word it in your methods, that you're actually not analyzing all data in one shot. You can, but we're not going to do that kind of thing in this class. We're going to do each one as a separate test of the two samples, two populations in the pair. So in the end, you might wind up with something like this. So the compact, they're not very different, but they're different enough to be statistically significant. And we've set our alpha, let's say, at the p.05. We're willing to make an error calling those two different 5% of the time, when in fact they weren't. Okay? I'm not going to get into alpha and p and all that, but that's what this little image suggests, that they're different. They're different enough. Ecologists are good with 5% errors. Okay? This one is more like only 1% different, right? So that one, increasingly, those two are statistically significantly different. And then when you use 3 asterisks by convention, that usually means that you're at p.001 or only 0.01% different in your between the two data sets. So always better, but this is good enough for most ecological applications. It's a messy world out there, so I'm very happy if I can reject the null at 0.05, right? In fact, sometimes I get 0.06 and I say, well, it's getting close and that's good enough for me, and I explain why I feel that way. Just how ecology works. Okay. This is a good place for me to take a break. Let me lead into that break with this little slide. This is a cup from the Ig Nobel Award celebration. It happens most years, probably won't happen this year. This is given to people who come up with the brilliant idea of putting a nitroglycerin-powered rocket on their car and then drive down a road and didn't realize that it would get going so fast that they actually can't turn the corner and they go off the cliff and unfortunately total their car and probably their bodies. Every year there's the Ig Nobel Awards. Look for it on the web if you can for some humor. But when they give these Ig Nobel awards, the people that win them give these really long, drawn-out speeches about all sorts of trivia, and it goes on. And finally, there's a young lady, girl, I don't know, probably preteen, maybe teenager, who walks out and starts saying this: "Please stop, I'm bored. Please stop, I'm bored. Please stop, I'm bored, please." So I figure this is a good spot to stop before I dig into yet some more trivia about data analyses. And so we'll do that on the next segment. Give yourself a chance to shake off some of the cobwebs and come back in with a fresh mind. So we'll see you next time. Thank you so much. Cheers.